we've been talking a lot about kind of this defining question of AI, machine learning, that like, what do these probabilities mean, right? Like these individual probabilities for the non-repeatable events. And don't worry, I don't have like a complete answer to the question. The question remains a question. But I do want to give theoretical sort of cryptographic or complexity theoretic perspective on this question. And the perspective is going to be in terms of computational indistinguishability. So what is computational indistinguishability? Where does it come from? What does it deal with? And how does it apply to our question about fairness or accuracy in machine learning? So if we think about tossing a coin, then one way of looking at the coin toss is to say, okay, if it's a balanced coin, it's going to be, once the coin is up in the air, it's a 50-50 shot. Is it going to come up heads or tails, right? That's very intuitive to all of us. But we could also think about this as a question of computational resources and information. So when the coin is in the air, if we sort of have a gazillion cameras all around the room, hooked up looking at the exact angle at which it's spinning, at the velocity, at the density, the friction from the air, and hooked up to a supercomputer that can run a really fast computation, maybe we can predict with certainty that the coin is either going to come up heads, 0, or tails, 1. Right? So from this perspective, which is very natural from a complexity theoretic point of view, the question of probabilities is a question of resources. It's a question of computational resources and information, right? Do we have all of the features of the coin in order to compute whether it's going to come up heads or tails? And do we have the computational power to run that complex computation? So I sort of want to go with that today and talk about these probabilities as a question of computational resources, and to some extent, if we don't have the cameras and we don't have the supercomputers, then yes, the coin toss, it might be deterministic. It might all be kind of determined once the coin is up in the air, but from our perspective, it's indistinguishable from random. Okay, so that's a pretty good answer for what we mean when we say it's a random coin flip. We cannot distinguish it from truly random. So our goal, we have our P star, the correct probability that an individual is going to develop heart disease. Okay, that's how we define P star. And we want to approximate it from sampled outcomes. And we expect that we don't have neither all of the features in the environment and in the universe to sort of deterministically say whether the individual will develop heart disease, and we also don't have the computational resources. So what I want to say is that if the situation is that we cannot distinguish, it's just impossible, given the information we have and the computational resources we have, to distinguish whether the probabilities exist or whether everything is 0 or 1, then we can say that, there is a probability. And that's a pretty good situation to be in, because no one can sort of distinguish between the probability that we are estimating and the truth, right? It's just impossible, given the information we have. So just to make it concrete, like if we have our world, this is our people, this is people in the world, and some will develop heart disease and some will not. And it might be the case that if we knew everything in the universe and we had all the computing power in the universe, we could decide, or we could actually calculate who will and will not deterministically develop heart disease in the next 10 years. But if it's impossible, if we cannot distinguish the zeros from the ones at all, and half the people will develop the condition and half will not, then just saying a half for everyone is indistinguishable from the truth, right? No one can distinguish the zeros from the ones, and so saying a half for everyone is sort of a good approximation, or is the best we can do. So that's going to be the perspective that I want to talk about today, and it's this notion of outcome indistinguishability. For risk predictors. So So what do I mean when I say indistinguishability? Just a quick detour. Yep.
So in the left circle that you drew, are you assuming everyone in that has the same feature vector?
Yeah, we have the same feature. They don't have the same features. They don't have the same setting. There's the same features. Maybe we have age and medical history, but they're not all identical.
Okay.
But nonetheless, you can't distinguish the zeros from the ones.
So, but instead of giving the same probability to everyone, can't we do better by dividing them into equivalence classes based on their feature vector values, and then giving a different probability to each particular?
So I don't know how to do it, and it might be computationally completely infeasible. So it might be, if you just look at singletons, you either see a 0 or a 1. So I don't know, like, there's nothing to average over. And you cannot identify a set where the fraction of zeros is very far away from a half. Like, it exists, but it is computationally hard to identify from the features. It might exist, but it's computationally hard to identify from the features. So indistinguishability, we have, when we talk about two distributions, we say that they're indistinguishable to a distinguisher A. So we'll say that they're epsilon indistinguishable to a distinguisher A. This is for two distributions D0 and D1. So we say that the advantage of A in distinguishing between D0 and D1 is the difference between the probability over Z sampled from D0 that A says yes or says 1 on D, and the probability over Z drawn from D1 that A says yes on Z. Okay, so if the probability that the distinguisher A is trying to say 1, say with higher probability when it gets examples from D0 than when it gets examples from D1, and if it cannot do this, if it can't distinguish them, if it can't have a meaningful gap in the probabilities, then we say that the two distributions are indistinguishable to the predictor, to the distinguisher A. Okay, so we want that the advantage of A distinguishing between D0 and D1 will be at most epsilon. And we could talk about being epsilon indistinguishable to a class. This is a very fancy A, so it includes a lot of distinguishers A. And that just means that for every distinguisher in the class, the advantage of distinguishing between the two distributions is at most epsilon. Okay. And sometimes we'll just say something like D0 and D1 are indistinguishable by the class A with advantage more than epsilon. And this is a really helpful notion. The notion of indistinguishable distributions is really helpful in cryptography, in complexity theory. We often talk about pseudo-random distributions. So these are distributions that are very far away from being, say, uniformly random over their support, but cannot be distinguished. So maybe it's a distribution that has small support, but it cannot be distinguished in polynomial time by any efficient distinguisher from a truly random distribution. So there's a lot of theory in pseudo-randomness in cryptography about constructing such pseudo-random distributions, and we want to take this methodology or this notion of indistinguishability of distributions and apply it to the setting of predicting risk, of risk prediction for individuals. Okay. So what I really want to say here is that if my predictions, if I'm predicting a half for everyone, but the situation really is indistinguishable, the reality of zeros and ones is indistinguishable from my predictions, then I'm pretty happy. We'll be in pretty good shape. Okay, if it's indistinguishable to a large class of distinguishers. Okay, so in particular, yeah. So that's sort of what I want. Another way of looking at it is if the distribution of zeros, of features that will end up being zeros, is indistinguishable from the distribution of features that will end up being ones, then these two worlds are indistinguishable. And again, saying a half for everyone is a pretty good approximation. Okay. So in particular, and I'll get back to this point, if these two views of the world, and we'll make it formal in a little bit what I mean here by the view of the world, what does a distinguisher get to see. But if the sort of hypothesized view of the world, where everyone is a half, is indistinguishable from the real view, in a way that means that it is irrefutable. No one can come up with a way of distinguishing what I claim are the probabilities from reality, and so my claims about the probability are sort of a really good approximation or a really good theory of how the world works. Yes?
Yeah. Can you say again what you mean by, what it means for a distribution to be random?
Yeah.
What's the question?
What does it mean for a distribution to be random? So, yeah, so I'm going to talk about what the distributions are over here in a minute, but when I was talking about cryptography and pseudo-randomness, what I meant is that we try to come up with a distribution D, say, over 0, 1 to the n, whose support is much, much smaller than 2 to the n, but nonetheless it is indistinguishable from just a uniform distribution over all 2 to the n possible outcomes. Okay, and under standard cryptographic assumptions or complexity theoretic assumptions, we can actually construct such distributions, at least in the theory of in the theory and the practice of cryptography.
So in the, are we assuming that everyone has an inherent true deterministic label, or could there also be some inherent randomness?
Yeah, we're not assuming anything. There could be inherent randomness. And all I'm saying is that, this I'm taking it to the extreme. Even though there is no inherent randomness, and I am giving a half to everyone, I still think of that as a good model for how the world is working, for how, these outcomes are being generated, so long as it cannot be distinguished from reality. Okay, so it might be here that there are some, maybe it's 2/3 and 1/3, other way around. And I'm giving a half to everyone. And I'm still, pretty happy so long as no one can distinguish the 2/3 from the 1/3. Okay, so make this a little bit more concrete. Really, what we're thinking about is this p tilde of x, which is giving us a probability. You can really think of that as a generative model for outcomes, right? It's a model that tells us how the Boolean outcome for individual x should look. It should be a Bernoulli, p tilde of x is telling us this should be a Bernoulli random variable with bias p tilde of x, probability p tilde of x of being 1. Okay. So really think about this as our hypothesis, our model, our hypothesis. This is the hypothesized probability that x will see outcome 1. Okay? And you could think about the distribution, let's call it d tilde, where you sample x according to d, and then you sample the outcome according to p tilde of x. And p tilde is hypothesizing that this is the distribution of the world. This is how the world works. In reality, so this is sort of the hypothesized distribution. And reality is different, or might be different. Right? In reality, we have x drawn from the distribution d, and then we have y star drawn by p star of x, the correct probability, which might not even be a probability. It might be 0 or 1. So these are two distributions. And when I talk about outcome indistinguishability, what I want, at least one variant of outcome indistinguishability, is I want for these two distributions to be indistinguishable with advantage greater than epsilon. Okay. And if we can achieve this, then I claim that's a strong notion of meaningfulness for our probabilities, right? No one can distinguish between our hypothesized model of how reality works and the real way that reality works. So we're doing pretty well. Maybe if they get more features, they'll be able to distinguish. Maybe if they use a stronger class of distinguishers, they'll be able to distinguish. But within this class and with these features, the distributions cannot be distinguished. Okay, so is that clear? Excellent. So let me just write. So here we have our hypothesized distribution. And here we have reality. And they are indistinguishable. So is there anything more we could hope for? We'd like them to be equal, but we do think that P star might be out of reach. So for them to be equal, P tilde needs to equal P star. And maybe sometimes that's possible. But often, or in many interesting cases, it is not. But think about what the distinguisher gets to see here. Right there, we have our predictor P tilde. And we're not letting the distinguisher here actually see P tilde of x. We're just giving it a sample, drawn according to either P tilde of x or P star of x. And this is what we call no access outcome indistinguishability, or OI. And we could make the notion stronger by giving the distinguisher also access to the predicted probabilities. We call that sample access. So in the hypothesized distribution, which is what, in the hypothesized distribution, we see x. I'm going to drop the d. We see y tilde that's drawn from P tilde of x. Sorry, we see P tilde of x, the actual prediction. And then we see y tilde drawn by P tilde of x. And then what will we see in reality? So we'll see the same x. And we'll see y star, which are the real outcomes. And so do I want a P star here or a P tilde here? It's a multiple choice question. Exactly. We don't have P star. It doesn't make sense to have P star here. So really what we're saying, or what we want, is that given this model, the model is P tilde. That's what we have in our hands. P star is somewhere in the world. I don't know who knows it. I certainly don't. We have P tilde. It is being examined. And the examiner, the distinguisher, is trying to reject it. It's trying to tell us, no, this P tilde is bad. The outcomes y star that we're seeing in the world are not coming from P tilde. And we want it to fail, right? It cannot distinguish between the case that P tilde really is governing how the world works and the situation where P star is governing how the world works. And notice that we could have indistinguishability. This is going back to the question here. We could have even if P tilde is very far, this might seem too strong, but it's not. We can have indistinguishability even though P tilde is really far away from P star. It's still indistinguishable, say, to polynomial time distinguishers. Okay, so that seems pretty good. Even if the distinguisher is looking at P tilde of x, it can't distinguish whether the outcomes are coming from that or from y star. Anything even stronger? So y star, we always have sample access to the real world. So real samples in the real world are governed by y star, right? Like, we see individuals and either they develop heart disease or they don't. In reality, that is our y star. So that's always our access to the underlying unknown distribution. We do get to see samples, labeled examples of samples drawn from D. We don't get to see P star, but for individual samples, historical samples, or a training set, we do get to see their labeled outcomes. Okay, so is that where it ends, or can we have even more fun? Yeah?
What's the difference between no access and sample access? Like in sample access, we have access to labeled examples. We have access to a training set. What's the difference between the first one and the second one? No access?
So we're giving more power to the distinguisher here. We're allowing it to examine not just x and y, which is either y tilde or y star, but it also knows what the predicted probability of P tilde on x is. Okay, so it will be harder. This is kind of like a stronger notion. It will potentially be harder to achieve.
For the, I guess the hypothesized, what we get to see from the hypothesized distribution in the sample access case, is that different than in the no access case? Because are you seeing?
No, we get the same. We're just getting to see it together. We're not just seeing the outcome, we're also seeing the distinguisher gets to examine. So think of it as like someone who's trying to examine the prediction software. Like, are they only getting labeled examples according to whatever the predictor is saying versus reality? Or do they also get to see the predicted probabilities together with an outcome that is either drawn according to those probabilities or according to reality?
So for the example, indistinguishability, does the distinguisher know the function P tilde?
Say again?
Does the distinguisher know the function P tilde?
Good, so it doesn't the way I wrote it, but we could imagine a stronger definition, an even stronger notion, where the distinguisher doesn't just get to know P tilde on X, it knows all of P tilde. Maybe it has oracle access to it, so it can come up with other inputs, X prime, and ask P tilde about them. Not just X, but any X prime that it wants, or maybe it even gets the code. So those are two stronger notions. So
I'm confused, actually. So P tilde and Y tilde are not the same thing? P tilde X and Y tilde?
no, so P tilde is a number between 0 and 1. That's the predicted probability. That's the predicted probability that P tilde thinks that X will, have a cardiac event, have a heart disease. And Y tilde is just a Bernoulli sample drawn according either to this probability or Y star according to the true probability. Okay, so this distinguisher gets an individual, it gets a predicted risk of heart disease, so it gets to see it's 0.2, and then it sees the outcome 0 or 1, which is either drawn according to 0.2 or drawn according to reality. And it's trying to distinguish the two situations.
But if you know P tilde X, you don't need to have X-ray information.
On this side, but on this side, that's exactly what I'm trying to do, right? Like I'm trying to understand. You're right that given P tilde of X, I can also generate samples according to Y tilde. What I'm trying, but I have one special sample that I care about that is, I don't know whether it's Y tilde or Y star, and that's what I'm trying to distinguish. Okay, so you're right that here I could draw many, many samples, as many as I want according to Y tilde, but I care about this one special sample that I've been given, and I'm trying to understand whether it's coming from reality or it's being generated according to the model. They're great questions. Okay, so oracle access. I'm going to augment. I don't want to get too technical about oracle machines, but basically I allow the distinguisher to ask P tilde about the probability of any X that it wants in the world. Okay, not just the X at hand. That's the notation for giving it oracle access to the predictor. And I want indistinguishability of the same two distributions. Now, you might object and say that I don't need to have P tilde in here because the distinguisher can compute it by itself, and you would be right, but I think it's clearer if we don't omit. I want to clarify that this is a stronger notion. So the distinguisher is being given more power. It's harder to satisfy this notion. So having indistinguishability against such distinguishers is even stronger than having them against having indistinguishability for distinguishers that don't get oracle access to the predictor. And finally, I won't write more about it, but I just want to say we could instead here, the distinguisher is just getting oracle access to the predictor, so it can plug in X's and get out the predicted probability, but we can imagine even more scrutiny, so actually giving the distinguisher code access. One really important thing I want to emphasize for oracle access and code access, in both sides of the picture, the predictor is P tilde. P star, we do not know what it is. No one can see it. No one can get it. No one can try to distinguish it. The distinguisher has P tilde, and it's just trying to distinguish whether the outcome Y is being generated according to this P tilde or according to P star. Okay? But the actual predictions that we are getting, the probabilities that we are getting, the only ones we have access to are p tilde. The only ones we have explicit access to are p tilde. Good, so a couple of notes. So all of these definitions is a hierarchy of stronger and stronger definitions. They are parameterized by the distinguishing class, A, kind of the computational resources of the person who's trying to falsify the predictor, trying to find a way of distinguishing what we're predicting from reality and saying our predictions are bad. So the computational strength that they have and also the features of the representation are important, right? Maybe something is indistinguishable in polynomial time given a certain number of features, but if we add more features, it suddenly becomes very easy to distinguish it from reality. And that's actually a path towards progress. So that means that if we get those extra features and we are indistinguishable with respect to the richer class of features, we will be coming closer and closer to P star. Okay. So I guess I've been saying it implicitly, but I'll say it explicitly. One thing I really like about this indistinguishability is sort of thinking about it along the lines of the scientific method. So in the scientific method, what we usually do is we propose a scientific theory saying we believe this is how reality works, say in physics. And then, people can try to falsify our theory and say, no, here's an experiment, and look, your theory is predicting that something will happen, but in reality, something else is happening. So that's a distinguisher. The refutation really is a distinguisher between our model of how we think reality works and the way reality really works. And that's very much in line with what we're doing here. We're looking for predictions that are sort of irrefutable. Okay? Irrefutable within a certain complexity class and with certain features and up to advantage epsilon. Okay, so you might worry, this is like the running theme, that this is way too strong, right? Like irrefutable predictions, like we can't get them, but we can get them, and the way we get them is through a relationship with multi-calibration and multi-accuracy. Actually, there was something else that I wanted to say before going there, but hopefully that got you excited to hear more. So another thing you didn't object to is that the distinguisher only gets to see one example here. So think, for example, okay. So think, for example, about software that we are using in the criminal justice system. Okay, so some software company is proposing that we should use this software to estimate the risk of recidivism and use it in order to make decisions about people's personal freedom. And you might say, no, we should not use some software. We should not trust the software company X, and my heart is with you. But nonetheless, these software programs are being proposed. They're being used. And I think it's important to have a theory of how we audit them. So here we would be saying, at the very least, Oracle Accessoi would say the software company should at least allow us to probe the software, ask it questions, what it would do for person X or person X prime. Maybe we even ask that they release the code. And it also makes sense that we would ask for indistinguishability, not just for a single sample, one sample at a time, but maybe many samples, right? So I would want, if I'm going for sample access, I would want that even given x1 and p tilde of x1, and let's call this y tilde 1, and x2, and p tilde of x2, and y2, this should be indistinguishable from x1 p tilde 1, y star 1, x2 p tilde 2, y star 2. Sorry, apologies for my handwriting. Right, or if we get k examples, should still be indistinguishable. Right, so certainly, if we're indistinguishable for k examples, we will also be indistinguishable for one example. Right, the distinguisher can just ignore all but the first. And what about the other direction? So what I want to say, and I'll talk in a minute about sorry. I will talk in a minute about, I do have my notes, about what's possible and not possible over here on the left. But I want to say that going from single sample to multi-sample doesn't increase the power of the auditor by too much, okay? So in particular, if there is a multi-sample, if there is a k-sample distinguisher that has advantage epsilon, there will also be a single sample distinguisher that will have advantage something like epsilon over k. Okay, so single sample distinguishers are not much less powerful than multi-sample distinguishers, and I want to caveat, I won't, well, in the end, if you're very excited and you have energy, maybe we will show, maybe we can prove that, but the way you prove it is through a hybrid argument, and you show how to take any k-sample distinguisher, and using a little bit of extra information, you can transform it into a single sample distinguisher, and just the distinguishing advantage decreases by a multiplicative factor of k. Okay? So multi-sample distinguishers, if we can achieve single sample indistinguishability, we can also achieve multi-sample indistinguishability. That's a good takeaway. Okay, so I'm not going to focus too much on that distinction. Good. So what can and can't we achieve? The two boards next to each other, that's nice. So we can actually achieve all of these. Okay, so for any class of distinguishers and any epsilon that we want, there exists predictors achieving all of these notions of indistinguishability. Okay? And that goes back to the point I was saying. We can generate these p tildes that might be very, very far away from p star, but nonetheless, they are indistinguishable to the bounded class that we have in mind. Okay, so in particular, let me tell you something about the sample complexity of learning an indistinguishable predictor and the size or complexity of p tilde that we learn in the end. So for these two levels, for no access and sample access indistinguishability, we can achieve them, and the sample complexity is something like log the number of distinguishers you want to handle. If you have some other notion like VC dimension or Rademacher complexity of the class of distinguishers, that's something we can talk about. Maybe it's achievable. Divided by some polynomial in epsilon. It's not exactly the same polynomial for no access and sample access OI. And in fact, we can also achieve the stronger notions in small sample complexity. So oracle access, when the distinguisher gets to probe p tilde and code access, we can always achieve them using bounded sample complexity. So with oracle in sample access, the distinguisher just gets to see the prediction on one particular individual that was sampled. Okay, so the distinguisher gets an individual or a collection of individuals, their predicted probabilities, and their outcomes. Outcomes may be drawn according to p tilde or according to reality, p star. Whereas in oracle access, the distinguisher can ask questions about people who are not in the cohort at all that it receives. So it gets maybe to see one individual or a few individuals, but then it can also ask, what would the predictor say if this individual's thinking about criminal justice, if their record of prior arrests, instead of being this, was that? You can sort of tweak the examples it's looking at and see what p tilde would predict. It doesn't get to see y star for those hypothetical proposed modifications to the people, but it does get more access to the predictor itself. Okay, so it's more powerful, and as we'll see, that actually it is harder to achieve oracle access OI in a quantifiable sense. Yes?
In sample access, you're drawing to individuals from the distribution as well. So like
In all of them, the distributions are, the individuals x are always drawn from the correct underlying distribution D.
When like a company releases sample data or something, it's not necessarily like it could be like cherry picked, right?
Ah, excellent. So you should talk with Tal, who has some work on verifying using a few samples that the samples you're being given and the behavior that's being predicted is from the correct distribution and preventing cherry picking. But it's a good question.
I have a motivational question. So with all these indistinguishability guarantees, it only gives you very accurate predictor, but by no means it's going to give you fair.
Good. So the question is, okay, so this all seems to be accuracy or indistinguishability with respect to the distribution D, which is generating X and these labels Y star. What does it have to do with fairness? And I have two answers to this question. First, there are many settings. For example, the medical setting that we'll talk about, that Noah Dagan and Zayad will talk about tomorrow, where accuracy is fairness. Right? Like actually being able to accurately predict the risk of heart disease is a fairness question. It is not the only fairness question. There are biases in the data and there are biases in historical treatment, but there's also the question of actually being able to predict for diverse populations what is the correct risk of heart disease. And that is a fairness question, I think. So that's one answer, but I like your question very much, and I'm going to give you the same answer that I gave yesterday for multi-calibration, which is if we want to think about auditing the data for unfairness and potentially fixing unfairness in the data, a good starting point is to be able to understand what are the probabilities that are appearing in the data as it is, in a way that reflects subpopulations that is sort of indistinguishable from the truth, that is capturing the truth, or is capturing, I don't want to say the truth, is capturing the current reality in a good way. And then we can start thinking about affirmative action and corrective discrimination. Okay, so we can learn. The running time of the learning algorithms will be large, as it was for multi-calibration, and you'll see in a minute it's for good reason. I just want to say that the complexity of the predictors that you actually, once you talk about generating this actual predictor, so the mapping that takes X and predicts the probability of the outcome being 1, there's a big difference between the first two levels here, no axis and sample axis, and oracle axis or code axis. So here, the predictor can be very, very simple. So the size grows polynomially with the desired indistinguishability times the size of predictors in the class A. Okay, so that's analogously to what we had with multi-calibration, where in the end, the predictor was sort of just taking like a collection of sets and nudging them. Generating the predictions wasn't much more complicated than identifying the sets. And here, generating the predictions is not going to be much more complicated than evaluating the distinguishers. But once we want oracle access or code access, the situation is quite different. And the predictors start to grow exponentially with our desired indistinguishability. I think this is right. Is it size of A to the 1 over epsilon? It doesn't, close enough. Okay, so I need to think over the break whether it's even worse than this. Maybe it's size of A to the 1 over epsilon. Maybe it's 2 to the 1 over epsilon times size of A. Suddenly, I'm worried that I have it a little bit inaccurate. In any case, instead of growing polynomially with 1 over epsilon, the size of the predictor is growing exponentially with our desired indistinguishability. So really, this becomes infeasible quite quickly if you want good indistinguishability, if you want to guarantee good indistinguishability. Okay, so I would say it's semi-feasible. It's not fully feasible, but it's feasible for large epsilon, and this is inherent. So under standard complexity assumptions, there are data distributions where you cannot do better than this. There are data distributions and classes of distinguishers where you cannot do better than this. Okay, so it's a real cost. And in some sense, it's bad news, right? Like, it's expensive to get these advanced notions of indistinguishability. And on the other hand, I think it's good news, or it's teaching us something. It's really telling us that the power of distinguishers who are able to probe the software and look at what it's doing, those are harder to fool. You need to work harder to actually convince them, and that's a good thing. We want the predictor to need to work hard. We want to have convincing predictions. Okay. Good. Questions about that? So I would like to give some intuition for how we get these results. And it all has to do with the types of algorithms we saw yesterday and we've been talking about today for achieving multi-accuracy and multi-calibration. So in fact, no-access indistinguishability is very tightly connected to multi-accuracy, by which I mean if you want to have indistinguishability for a collection of distinguishers, that is equivalent to trying to achieve multi-accuracy for a certain collection of sets that is tightly related to the distinguishers. There's an equivalence there. For sample access OI, it's strongly connected to multi-calibration. Okay, so for any class of distinguishers for which you want indistinguishability, there's a collection of sets so that roughly calibration, multi-calibration on that collection of sets is equivalent to sample access OI for that collection of distinguishers. And also the more advanced notions of indistinguishability, I guess we couldn't even conceive of them before we had this language of indistinguishability. You could come up with sort of enhancements to multi-calibration that capture them. Let me just say that the algorithms we have for actually learning these types of things are similar in spirit to the multi-accuracy and multi-calibration algorithm. So we start with a certain predictor. We look within our class of distinguishers to see if they can distinguish between, data generated according to the current predictor and the real data. And if we find a distinguisher in our class that can distinguish, then we fix our predictions and we make progress. Okay, so it's a similar flavor of algorithm. But notice that it's circular again, in the same way that multi-calibration was a little bit circular, that the more complicated the predictor gets, the more complicated the distinguishers get, and this is where the exponential behavior is coming from, in a nutshell. So I thought what I would do, I'm actually going to leave that as a, either for, if you're really excited and before going for the break, you want to see the equivalence between no-access OI and multi-accuracy, then we can do it. But in the interest of time, let me leave that. I think that's at the level of, you should really think about it. It can be a homework assignment to come up. So you're given a collection of distinguishers A, and now define a collection of sets so that multi-accuracy for that collection of sets implies indistinguishability for the collection of distinguishers. Okay, so something to think about. And if you have trouble, then you can look at the paper. On outcome indistinguishability, I should say, this is work with Cynthia, Michael Kim, Omer Reingold, and Gal Yona. And the thing I really want to spend the rest of my time on is, we've talked about indistinguishability. It looks powerful, but is it too strong? Do we really care? What does it give us? So I want to give an application of indistinguishability, and in particular going back to fairness, to show that it somehow, to me at least, it has a flavor of universality. This is essentially giving us everything we could hope for in terms of fidelity of the predictions to the data. Okay. So for that, let me erase actually over here. I want to go back to fairness. And we talked about multi-calibration and multi-accuracy. And we didn't really talk about how they relate to pack learning and loss minimization. Okay, well, we talked about it from a complexity theoretic perspective. But now I want to talk a bit about it kind of in terms of, these are different solution concepts for what you might want from a predictor. Do we want it to minimize some loss, or do we want it to produce calibrated predictions? Or maybe we want it to be indistinguishable, and how are all of these connected to each other? Like, what's better, what's worse? Cynthia will speak about it more. in the next hour, but I want to say something about it from the perspective of fairness. Okay, so in pack learning, usually we're looking at the loss of a certain predictor, p tilde. And we're usually decomposing that as the expectation of some loss function like the squared loss or something like that between the predictions, the predicted probability of x, and the true labels y. So one popular option is to take the squared loss, p tilde of x minus y squared, and look at its expectation. And then we want to compare that to some benchmark class. Okay, so we want to be doing no worse than the best classifier in some class big H, up to some epsilon. Okay, so that's agnostic pack learning for risk prediction, which we talked about. And we said that this is a global measure of loss, so it's missing the subgroups, or it's missing, the errors could be adversely concentrated on some protected group. So it's very natural to talk about multigroup pack learning. Where we would have a collection of sets in the way that we've been thinking about so far, and we would want this guarantee, so not only is our predictor, competitive with the best in some class, in some benchmark class globally, but actually also for each and every subgroup, we are achieving good loss compared with a benchmark class. Okay, so for every set in a rich collection C, the loss, so I think of D sub S as the distribution D restricted to members of S. Okay, and I want that the loss of the predictor on every subgroup is competitive with the best in the class on this subgroup. Okay, so for every subgroup, the predictions that they're getting are not worse in terms of their loss than whatever the subgroup's favorite predictor in this class H would have been. Right? So different subgroups might have different favorite predictors, and we are competitive with all of them simultaneously. I should say plus some epsilon. And you could even think, I won't do it, but you could think about every group selecting its own benchmark class. We can achieve that as well, but I won't talk about it today. Okay? So that's great, or that's something we may want to achieve. And how does it compare to multi-calibration? Or how does it compare to indistinguishability? So what I want to say today is that indistinguishability actually gives us a unifying framework for obtaining these multi-X guarantees. And in fact, we can get multi-group pack learning sort of directly from indistinguishability for an appropriate class of distinguishers. That's the main result I sort of want to leave you with. Now, I do want to generalize this. So here we have in agnostic learning, usually we talk about loss functions that get the prediction and the label y. We call these decomposable loss functions. So we're just looking at the expectation over individuals of the loss experienced by each individual. And that doesn't capture things like calibration, right? Calibration is not captured by decomposing the loss into what happens for individuals. It's sort of what's happening in aggregate, right? Maybe for some of the people for whom I predicted a half, the result was 1. For some, the result was 0, but I'll be calibrated in total, okay? So I want to generalize our notion of a loss function to anything that we can measure sort of using a sample from the underlying distribution. Okay, so it'll be the expectation over drawing some m samples from the underlying distribution of the loss of some loss function, a general loss function that's computed on all of these individuals and their predicted probabilities and the actual value y seen. So now, this notion of a loss function, which is more general than what's done in the agnostic learning literature usually, that allows me to capture things like calibration, right? I can check whether my predictions are calibrated on a large enough sample from the distribution, and if they are, then they will also be calibrated on the underlying distribution. It's letting us capture other things like false positive rates, false negative rates. Maybe the loss will also have to do with fairness, so it will be some combination of how accurate the predictions are and also how many fairness violations there are with respect to some underlying metric. So quite a very general notion of loss. And I want to ask for which kinds of loss, so these, yeah.
So just to clarify, the difference in your notion here is that you're adding xi as one of the arguments?
I'm both adding xi and I'm not just taking the expectation.
I can't see it because of the glare.
I'm not just taking the expectation, but I have some more complicated function that is we're looking at the entire sample together and deciding what the loss is. So for example, here I could be looking at the entire sample and asking, are the predictions calibrated? And there's no way of expressing that up here. Okay, so I think of this as kind of a unifying framework for thinking both about things like the squared loss that we think about in agnostic pack learning, but also calibration and even things from the fairness literature. Okay, and now the question I want to ask is, for which kinds of loss functions can we achieve this multi-group type of pack learning or loss minimization? And I want to say that it doesn't always make sense, but it often makes sense, and when it makes sense, we can achieve it. So why do I want to say that it doesn't always make sense as a goal? So the reason is that I want to handle a very general notion of loss functions. It captures calibration and it captures squared loss, but it also can capture things for which it doesn't make sense. So suppose we have two groups in our population, and here the loss function for this group, the loss function really wants their predictions to be 1. So the loss function just ignores y, and it says on this whole group you have to predict 1, 1, 1, 1, 1. But on the red group, the loss function says, if you have a bunch of members of the red group, your loss has to be 0, 0, 0, 0, 0. So we can't make both groups happy, right? The individuals that are, either we have zeros here or ones here, and then the members of the group S will want everything to be 1. The members of the group T will want the predictor that gives everything 0, and we won't be able to make we won't be able to make both of them happy. But it's also kind of like it's a loss function that doesn't depend on what the sort of individuals want. It says that, for the same individual, when they're looking at their membership in different groups, wants different things. I don't know, maybe that makes sense, but mathematically, if that's the case, then I can't guarantee that all the groups are happy. Okay, so instead, what I want is to talk about, I guess I shouldn't have erased it, what we call it an F proper. I'll write it up here. Loss functions, where all this means is that there are really what the individuals want is for their predicted probabilities to be in line with P star, okay, with the correct values. So notions that are geared towards, notions that are geared towards accuracy. For today, we have a more general statement in the paper. So there exists some function such that the loss is always minimized. Well, certainly the expected loss experienced by any distribution, no matter what the distribution is, the expected loss is minimized by predicting f of P star. For every x, we want to predict f of P star of x. Okay, so that's a natural notion. So if we're talking about calibration, wanting the predictions to be calibrated, what should we predict according to? What's kind of the ideal? So P star always gives us the most calibrated thing we could hope for. Okay, so that's just with f being, that's an f proper loss function with f being the identity function. If we're talking about the squared loss, trying to minimize the expectation of our p tilde minus y quantity squared, what's the ideal thing to predict? P star, someone said it, right? That's a statement that's not so hard to show. If you want to minimize the squared loss, you want to minimize the expectation of p tilde minus y quantity squared. The best thing to do is to actually predict according to the correct probabilities. If you want to minimize the L1 loss, the absolute distance between p tilde and y, then the best thing to do is to take p star and round it either to 1 or 0. If it's above a half, you say 1. If it's below a half, you say 0. So that's your f for the L1 loss. Okay. So I'm assuming that if we had the correct probabilities, p star, we could generate kind of the loss minimizing predictions. And now the theorem that I want to show is that for any such loss function, and for any collection of sets we have, we can minimize, and for any benchmark class H, we can be competitive for every group in our collection S, we can be competitive with the best hypothesis in H for that group simultaneously for all the groups. Okay. So for every F proper loss, this is work with Galiona. Multipack is achievable. Using the number of samples that depends on the size, logarithmically on the size of the collection of sets and the size of our benchmark hypothesis class. Divided by epsilon squared, whatever, or poly epsilon, whatever the epsilon you want is. Okay, so I think it's a cool theorem. The meta point I want to impress on you is that the way we will prove it will be through a simple is in the eye of the beholder, so you tell me if it's simple, but it'll be a direct reduction to OI, and we'll immediately get this strong, robust notion. Okay, so to me at least, it's a demonstration of kind of the universality or the power of this outcome indistinguishability framework, and we will see other examples of this in the next talk, in the next hour when Cynthia speaks. Okay. So how do we prove this? Basically, what I want to show you is that we can come up, given the collection of set C and the benchmark class H, we can come up with a collection of distinguishers, and OI will immediately imply that we are good loss minimization behavior. Okay. So fix the collection of set C and our benchmark class H. And now let's define a collection of distinguishers for every set S and for every hypothesis A, little h, in the collection and the benchmark class. We have a distinguisher. And it'll be a multi-sample distinguishers, so it gets whatever number of samples we need in order to compute the loss function. Remember, it's an F proper loss, so we get a sample, and for any sample drawn from the distribution, we can compute its loss. So the distinguisher accepts if and only if the loss, so it computes the loss according to p tilde, and it computes according to samples drawn by p tilde, or according to samples drawn according to the y that it sees, and that's how it determines whether to accept or not. So we compare the loss according to the xi's and p tilde and the y's that we got, right? We don't know whether the y's are y tilde or y star. And we want to make sure that the loss is not larger than the loss of our benchmark class, little h. Then our benchmark hypothesis, little h. And this loss is over samples drawn from the set S. Okay. H is it's hardwired. So we have a distinguisher for every set S and every hypothesis H. So this is a fixed H for this distinguisher, and that's what this distinguisher checks.
But f of p I tilde is what? Oh, that's also a function.
Yeah, so f is fixed. It's for the loss function. And the distinguisher is getting xi's and p tildes and y's. That's what a distinguisher...
The distinguisher is seeing a triple. Xi is a data element. The second thing is a number. What is the second thing?
Yeah, so the input to the distinguisher... Sorry. No, it's good. So if you're... Yeah. So the distinguisher, as any OI distinguisher gets, it's a multi-sample distinguisher. So it gets m samples x1 up to xm. It gets m probabilities p tilde of x1 up to p tilde of xm. Okay, so it's a sample access distinguisher. And it gets m y's, y1 up to ym. And it's trying to determine whether these y's are coming from p tilde or whether they are y stars. Okay? So this is just a distinguisher, and I'm saying we are going to have such a distinguisher for every set in the collection and for every hypothesis in our benchmark class. And now my claim is that if we have OI, if we have a predictor p tilde that is OI for this distinguisher, then it is minimizing the loss for every set in the collection simultaneously. And why is that? Well, imagine that the y's are drawn according to y tilde. If the y's are drawn according to y tilde, then we know that the best thing we can do is to predict according to f of whatever is generating these y's. That's p tilde. So certainly the loss here will be smaller, right? Because nothing is better than f of p tilde in this case. And in particular, h is not going to be better than f of p tilde. So all of these distinguishers are always, or with high probability, going to accept when the data are drawn according to p tilde. Okay, so in the hypothesized world, the distinguisher always accepts. But we said that the predictor is OI. So if we accept in the hypothesized world, we have to accept in the real world as well. Okay, so that means that also when the y's are drawn according to y star, the left-hand side has to be smaller than the right-hand side, almost surely, because the distinguisher has to accept. And what does that mean? That means that the real loss of f of the p tilde that we have, is smaller than the loss of h on the real data, which is exactly what we wanted, and this is happening for all sets in our collection and for all benchmark hypotheses H simultaneously, so we're getting our loss minimization guarantee. Okay, so directly, we had the power of OI in our minds, and directly we were able to transform any collection of sets and any benchmark that we wanted, and the benchmarks could be different for different sets in the collection. And immediately, if we're able to achieve OI, and we are because we have an algorithm for OI, then we also achieve loss minimization for these general loss, for any loss function that we want. Good, okay, so that's an exciting time to take a break, and you can ask me questions over the break, and let's reconvene at 3:35. We'll take another couple of minutes.